Without any further delay, I'd like to introduce today's speaker, Dr. Brian Kent. Brian is the Director of Science Communications as well as a scientist at the National Radio Astronomy Observatory. Brian received his PhD in Astronomy and Space Sciences from Cornell University, with his subsequent publications and studies in astrophysics and computing, including science visualizations of a variety of theoretical and observational phenomena. As well as his astrophysics research, Brian has quite literally written the book on visualization of data using Blender, and he is interested in visualizing data for scientific analysis, as well as reaching a broad audience with the visuals that modern 3D graphics can provide. His talk today will walk you through how to use Blender to start your workflow towards data visualization and rendering in 3D. So I know everyone's waiting, and I'll hand over to Brian.
Thank you very much, George. I'm going to go ahead and start by sharing my screen. And you should be able to see my slides now. So hello, everyone, wherever you're dialing in from. I hope that everyone is well. I'm Brian Kent from the NRAO in Charlottesville, Virginia. My contact and social media information are on the title slide. And what I will do is on the chat, I will put a link to the GitHub repository where you can find all the materials for today's talk. So you should be able to see that in the webinar chat. I want to acknowledge my parent organization and funding agencies. The National Radio Astronomy Observatory is a facility of the National Science Foundation operated under cooperative agreement by Associated Universities Incorporated. I encourage you to visit the NRAO Science website, which I will also put in the chat to learn about the exciting science that our radio telescopes facilitate. It's just science.nrao.edu. So a big thanks to George for reaching out for me to do this. It's our hope that this will provide some utility to folks in our science community. Thanks to all of you for taking out the time out of your schedule to attend and listen. I'm always interested in forming new collaborations with people in different areas of science. So there are many excellent visualization software packages and tools out there for people in the sciences to use. In the graphics industry, Maya, 3D Studio Max, and Houdini are incredibly powerful tools. For students and researchers, like many of the folks listening online today, Blender is a powerful option that you should consider. Blender is not designed as a traditional scientific visualization tool, but because its scripting interface uses Python, and many of us in science use Python, it deserves serious examination. In my field of astronomy, Python is heavily used thanks to the AstroPy project. So there might be some Blender users in our session today. For those new to the package, I hope this will be a useful introduction. We will by no means cover the entire interface. There are plenty of great resources out there. I have a number of links on the Git repository and in the PDF tutorials that we'll be going through today. So don't feel the need to follow every single step while I'm talking. That's why I provide the PDF files so that you can recap what we did after today's session. So as we go through the tutorials today, think about how it might apply to your work and the kinds of science that you work on. What kind of message are you trying to convey with your data visualization? Is it something diagnostic or phenomenological? Is it a technical or aesthetic piece that you're trying to create? And who is your audience? Is it a general public audience for education and public outreach? Or is it something for a scientific conference? So think about your own data today as I go through some of the examples. Many of the examples that I show you come from an astronomy background, but that doesn't mean that they won't apply to the kinds of things that you work on. If you have downloaded Blender and you want to follow along, that's great. If you just want to watch and listen, that's perfectly fine too. All the information is contained in the PDF files. And this is the general workflow that I like to think about as we do this and that you'll be following in the tutorials today. It's how I like to think of how we can approach to building a visualization scene. We have our actual scene, the boundaries of which we're going to operate. We're going to build models. We'll work with literally lights, camera, action. So we'll have our lighting and our cameras to manipulate in our visualization scene. And then what kinds of outputs do we want to have? Do we want to have an animation or high resolution video? What do we want to render out? So that's the kind of workflow that I think about. The tutorial procedure that we're going to follow, we're going to be working through a number of simple tutorials. And in those tutorials, I want to point out different Blender interface features and workflows. My goal here is to introduce you to the interface with these simple examples. The Blender files that I provided on the Git repository, those are going to be our end products. So you can always go look at what we actually created. All that we need to do here is to actually start up Blender. We'll always begin from the default file. I will be doing this on a Mac, but I do use Blender on my Linux desktop and in Windows as well. I've tried to make today's tutorials as operating system independent as possible. If you're working on anything, not only during our webinar today, but in the future, please save your work as we go through the demo. If you're following along, I always have to remind myself to do that. So make sure that you save things as we go along. But the tutorial procedure will talk about how we create models, how we import different kinds of data, and that's usually where a lot of our effort goes you know, how are we going to import different data formats, but Python thankfully takes care of a lot of that for us, how we can set up our cameras and do our animation, and then how we're going to render our output. So there are two different tutorials, and I'll give some other smaller examples here at the beginning as I introduce the interface. But the first one is a three-dimensional catalog rendering. I happen to be rendering galaxies because that's what I like to study. And then the second one is actually a three-dimensional transparent rendering of a data cube. And so I'm going to switch windows here and move over to the Blender interface. So I'll stop the share, and then I'll share a different screen. And hopefully you should see the default Blender interface. So if you start up Blender, this is what you will see. I'm using Blender version 3.5. Anything around that version number will be fine for this demonstration. And this is what it looks like when you start things up. You can customize the interface in terms of a light interface or a dark, any way you want it, depending on how your system is set up. A note for Mac users, if any of you are on a Mac like I am, and you're using a trackpad or a magic mouse, you'll want to change the preferences up here under the Edit menu. Okay, Edit and Preferences and Inputs, so you can rotate the 3D viewport. As you'll see today, and if you spend anywhere close to an hour working with Blender for the first time, there are multiple ways to manipulate and do everything. That depends on how you like to manipulate and how you like to manipulate things and how you actually want to develop your workflow. But there are three default objects and components that show up in your first file. The first is this cube-like object. That's what we call a mesh in Blender. We also have a camera. So if I click with my left mouse button, it will highlight orange. That's my camera. And then we also have a simple lighting element that is here in the upper right-hand corner. Okay. There are, and I can select any of these with my primary left mouse button. And there are different views in Blender. You can choose the different views at the top of the screen, depending on how you want to edit your scene and data. We will be using the layout right here at the top, the scripting over here on the right-hand side, and what's called the node compositor or the compositing tab here at the top. So I have a plugin in Blender called Screencast that will actually allow you to see what keys I am pressing in the lower left-hand corner of the screen here. So whenever I click my mouse, you'll see that button selected. If you'll see my middle mouse button, you'll see that selected as I rotate the screen. And then if I hit different key combinations, if I want to add a mesh, I can hit Shift A, and Shift A will show up in the lower left-hand corner of the screen. So on the replay, you can always go back and see what's going on there. So in this 3D viewport of Blender on the left-hand side, I have controls to manipulate the currently selected object, which happens to be the cube highlighted in orange. The annotations at the bottom of the screen tell you what the mouse will do in that current view. So I can select with my left mouse button, I can rotate with my middle mouse wheel, and then I can do an object context menu if I click the right mouse button. The mouse wheel zooms in and out of my scene. And if you're on a laptop, you won't have this, but if you have a regular desktop keyboard with a numeric keypad, you can press 1, 7, and 3, and that will rotate to the top, left, and bottom views, basically looking all 3 different sides of whatever visualization scene you happen to have open. And if I want to see what my camera is going to see, I can hit the 0 key, and that will show the camera view. You can do that if you have a full-size keyboard. Our 3D mouse pointer is the candy cane, very small little circle here in the middle of the screen. That's the location where we will place new mesh objects. I can add a new mesh object with a pop-up menu by hitting the Shift-A key. So if I hit Shift-A, a menu will pop up wherever my mouse pointer is, and then I can start adding different objects and models into my 3D visualization scene. I can also use the Add button here at the upper left-hand part of the screen. So I can manipulate an individual object, a mesh, a camera, a lighting element with the transform toolbar that slides out from the right-hand part of the screen. So if I hit this little caret arrow, I will get a transform menu, and this shows the exact location in this particular scene. Units are in meters. So I have X, Y, and Z, a rotation for X, Y, and Z, and then scaling in dimensions. So this allows for exact manual control and positioning of any object within the scene. And as you might imagine, this is also scriptable. All of these elements that I am clicking on here, you can access via Python and the scripting interface in Blender. I can also change the position of the 3D mouse pointer. I can lock the camera to wherever my eyeball happens to be looking in the scene at a given time. A mouse with a wheel makes things easiest, but you can use G, R, and S on your keyboard to grab, rotate, and scale, followed by X, Y, and Z to manipulate any currently selected mesh. So if I wanted to move this cube around, I can hit G, and now I can move it around. Control or Command Z will move it back and undo my last action. If I wanted to grab and move it only along the X-axis, which is this red line here, I can hit G followed by X, and now it's locked along the X-axis. Control Z to go back. If I hit G and Y or Z, I can move it along the Y or the Z axis. So I can also edit objects with the tab that will put me into edit mode. And now I can grab faces, edges, or vertices of any mesh object and manipulate and sculpt the object in that way. Tab takes me back to object mode. So the small icons on the right-hand side, I can switch to my camera view. I can switch between orthographic and perspective. I can pan and zoom. So in a perspective mode, all the lines converge to a vanishing point in the distance. In an orthographic mode, all of my lines are parallel. So hopefully you're seeing that difference there on the screen. If I want to zoom in and out, I can click on this zoom button and move my mouse in and out, same as the mouse wheel. And then if I want to pan the scene around, I can click on the little hand here in the right-hand corner. Okay, so different ways of manipulating the interface, and you get used to that very quickly. That's how the 3D viewport works. There are lots of different submenus that you can explore to manipulate it in different ways. In the upper right-hand corner, we have our scene outlier. This gives us a listing of our objects, any parent-child collection relationships that may exist between the objects, and any associated attributes associated with them. Each object right now, I just have 3 because this is the default file. I have a camera, a cube, and a light. And each one of these objects has a little eyeball and a camera. If I click on the eyeball, it will take it out of the viewport. If I click on the camera, it will stay in the viewport, but it will not be in the final render. So that allows me, if there are objects behind one another, I can take those in and out as I move around my 3D viewport. The A button on your keyboard selects everything. So right now, everything is selected orange. If I click off of that and click right now, just the cube is selected. On the right-hand side, we have the properties panels and tabs. This is where we control the properties and attributes of our scene and our current selected object. And we can control our final output resolution and frame rate, our global scene parameters, modifiers, constraints, materials, texture, and particles. We'll be using some of these menus in the demo, and I'll note that we're using what's called the default rendering engine known as Eevee for this visualization scenario. And if I click on this camera icon, I can see what my rendering engine is selected. There are different third-party renderers that you can also use with Blender, but we're just going to be using the internal default ones right now. And then this little printer output properties icon allows me to set my resolution. If you want to render in something in 4K, you can set a higher resolution. We've got it set to 1920 by 1080 right now. We can choose whether we're going to render out a static image, or if we're going to do a high resolution video, and what we want the compression to be, what we want the output, what we want the encoder to be for our video if you do any video editing, what we want our frame rate to be, because sometimes maybe we want to do something in slow motion. Anything that you can do and envision with animation or video, you can change in your output there. Okay. So, and finally, we have our animation player at the bottom, which shows our what we call our keyframe markers for camera movement when we get to that point in doing some of our visualization scenarios. So there's also a nice physics simulation feature that I want to point out. This is kind of a whole separate talk within itself, but one of the neat things you can do is you can do fluid and rigid body simulations. So if I have my cube right here, the first thing I can do is I can hit Shift-A and add a mesh plane. Then I can hit the S key and scale it. So now I have a cube and I have basically a flat surface that I want to utilize. So if I hit the cube with my left mouse button, it highlights orange. I grab it, hit the Z key, move it above the plane. So now I've got two objects, but I want to make them rigid bodies. So I'm going to left click and select my plane. And there's a little circular button here that if you hold over it, it will say physics properties. I can click on that, followed by rigid body, and change this. This is going to be my ground or my floor. So I'll make that a passive rigid body element. I'll change the surface response to have lower friction. And then I'll hire what they call the bounciness of the surface response. I can increase that a little bit just for this demo. And then I will click back with my left button on my cube, select a rigid body. We'll leave it as active. And now I've got some physical parameters like the mass that I can change. It's a dynamic object. I will lower the friction and again, increase the bounciness just so you can see it in this demo. And then if I go down to my animation tape deck down here at the bottom of the screen and hit the play button, you'll see that the brick and the cube in this case will fall. It'll bounce a couple times. And so this is how you start building a physics simulation using the parameters that are in Blender. I can also simulate fluids and gas. So well, I'm going to start a new file here and click on File in the upper left-hand corner and click New in General. I won't save it. And I'll start with my cube again. In this case, this is going to be the boundary condition domain of my fluid simulation. So if I hit the S key and scale the cube up, this is where my fluid will actually be able to exist. So I can go into my physics parameters again. Instead of clicking rigid body, I will click fluid. Okay, and I will set this to be a domain, and the cube will actually disappear, and there'll just be a wireframe that is left over. And we can turn on a number of parameters here. I'm going to change it to be a fluid or a liquid in this case. I'm going to turn on diffusion and mesh. And diffusion, if you click on these three small buttons on the right-hand side, it actually has presets of liquids of differing viscosities like water, oil, and honey, because those liquids are all going to react differently in a simulation like this. And then I can add a source of my liquid. So what I'm going to do is I'm going to hit Shift A one more time, and I'm going to hit and add another plane. It'll be right there in the center of my cube. I will hit G and Z and move it to the top. I will change this plane to be have a physics property of fluid, and I'll change it to be flow this time. And for the flow source, I'm going to set it to be the mesh and planar, but I'm going to change the flow type to liquid. I'll select is planar. And I will select the geometry, the flow behavior from geometry to inflow. And you'll see that a fluid simulation will start. And so this is acting as my source of liquid at the top, and it will run a very low resolution fluid dynamic simulation, all within the domain of the cube that I have set up. So there are lots of other parameters, as you can imagine, that you can change in something like this. I can change the resolution. Right now it's set to 32. If I increase that for a final render, it will be a much higher resolution. So these are just, I just wanted to point out the utility of doing different kinds of physics simulations. And as you can see from the physics parameters, you can do force fields, you can do collisions, you can do soft body dynamics, all sorts of different things that you can do in Blender, and it's a whole area to explore. But I just wanted to point that out before we start some of the tutorials. So lots of great features that you can explore. There are also plugins like Atomic Blender that allow a user to read in molecular database files and crystalline structures. So I've got an example of that. Let me open one here. And so here I've done just a read-in of a molecular database file, a PDB file, if any of you are familiar with that, of DNA. And this will allow Blender to render this out in 3D, so I can render out a real nice 4K video of whatever I have right here in my visualization scene. Okay. I can also manipulate my camera. So this particular view that we're looking at here of a DNA molecule is a quad view. So if I go to view and area, I can toggle my quad view and go in and out of that. So view, area, toggle quad view. So it now will show me a top, front, and right side orthographic view. And then I get a user perspective here in the upper right-hand corner. If I hit the 0 key or this camera button, I can show what my camera is actually going to see in my final render. So if I select the camera, you'll see the camera is selected right now. And let me move my top orthographic view and zoom into the camera. You'll notice that the camera has a normal vector pointing directly at the DNA molecule. And so I have the camera focused on my object of interest in this case. And down here on my animation bar, if I slide all the way back to the beginning, you'll notice that the camera is moving around the object. And I do this by inserting what are called keyframes. So at any point, if I want to mark during my animation where I want my camera to be located and pointed at, I can hit the I key and I'll get a context sensitive menu wherever my mouse pointer is, and I can keyframe the location, the rotation, the scale, or all three of whatever object I happen to be looking at. And so this allows me to build an animation and film my visualization scenario. And so if I zoom back out here, and I'm going to hit my Shift key and middle mouse button to zoom in on my example DNA molecule. If I hit the play button, if you watch in the upper right-hand corner, you'll see the camera moving around. And if you look in the top, bottom, and right orthographic views, you'll see the camera spinning around, but it stays focused on whatever object I happen to be looking at. So that gives you a lot of utility and creativity in allowing you to film your visualization scenes. Okay. So I'm going to start with a tutorial here with rendering a three-dimensional catalog. So I have the data loaded here, and the way that this is actually done is with Python. Okay, so what I've done in Blender is I've clicked in the upper right-hand corner on the scripting button, and this gives me a Python interface on the left-hand side. It gives me a small user perspective viewport in the upper left-hand corner. And then on the right-hand side in the middle of the viewport, I have a Python file that I have imported here. For those of you who work with Python a lot, you don't have to do it this way, but I'm just basically going to be using the Python CSV dictionary reader. I have a plain text file of galaxies, and in each line, each row for that file of the catalog, I have the name of the galaxy, a distance, and then an X, Y, Z position. So what we're going to do is we're going to build a three-dimensional scatter plot. I read that in with my dictionary reader, and there are some manipulations I have to do here in order to put it into a numerical Python array. And then what I can do is I can build a particle system and then manipulate the positions of those particles. This is a small catalog just for this demonstration. I have around 3,500 galaxies. I can set each of the where the frame start is going to be, where the end is going to be. I don't want the particles to disappear. And then I can actually change the positions of all of those particles by using the Blender Python module, which is BPY in this case. And there are different Python modules and libraries within the Blender Python module that allow me to set the positions of those particles. And then I have my galaxy catalog loaded, and then I can actually go through and film that catalog that I'm interested in. So this would work for any kind of three-dimensional scatter plot that you would want to load in your data. So I have a single Python function here called particle setter, and that is actually called by the Python script. I can go up and hit this little play button. I've already done that. That will run the script and that will load the data. Okay, so that's how the scripting interface works. If I go back to the upper left-hand corner and click on layout, I'm in my quad view again, and it might be a little hard to see over Zoom, so I will zoom in here, but I've got all of these little particles, and these particles each represent the position of a galaxy. So those are loaded here onto my scene collection in the upper right-hand corner. And if I click on my camera again, my camera has already been set with a number of keyframes. Okay, so if I go back to the beginning to frame one of the first frames here and hit the play button, you will see my camera moving around in the upper right-hand corner. And I'll show you what the final video output of this looks like when we finish the different tutorials. But this allows me to zoom around and film and animate my galaxy catalog. And the other element that I have is a plane element that is laid out in a grid. One of the things that you often find in doing a three-dimensional visualization scenario is you like to have some sort of reference for displacement and distances. So that way, when you play your video, people understand where things are moving around. So in this particular case, I've set up a grid of certain distances in astronomical units that will allow the user to see the relative motion of my catalog and where the galaxies are in reference to that grid. Okay, so that's something to keep in mind, especially if you're working with a large set of data that you're moving around very quickly. It helps to give your users that reference in your background. Okay, so that's one of the ways that we can actually load a catalog, build a grid, and then animate it with our camera in a visualization scenario like this. Okay, so that tutorial PDF is available on the GitHub repository that I put in the chat window. The second tutorial that I want to look at is different in that we want to look at three-dimensional transparent data cubes. So I'm going to open that file here. And right away, you will see that Blender looks a little different. And so what we're going to do is we're going to look at a boilerplate data cube of a CAT scan of a human head. All right. So this is a scan that was made. It's not super high resolution, so it loads very quickly. And I'll show you what these data actually look like. I'm going to stop my share and switch to yet another screen. So if I were to look at these data in 2 dimensions, and hopefully you can see this on your screen, I'm going to flip through this 2-dimensional movie. And what we're doing is we're moving through different slices as imaged from the CAT scan. Okay, so any imaging data that you can manipulate into slices like this, and we do this in astronomy all the time, you can load into Blender. So I'll switch back to the Blender interface here. And the way that we're going to load these data is using something called open shading language. This is an industry standard that I have a link to in the Git repository. It's a C-like language that allows you to read in this case, 3-dimensional data. So we're going to read our data in as a volumetric texture, okay? This is boilerplate code that is available in the cookbooks for open shading language. In this particular case, I'm going to read in, these happen to be TIFF files, but you could use JPEGs or PNGs. We're going to read in the data, and luckily Blender gives us as our default object a cube. And we're going to use this cube as our model holder and read in our volumetric data that is available in these image slices. So this is some OSL open shading language code here. I determine what the image number is going to be. I read in those files. And then what I do is I do a 3-dimensional texture of each file, and I layer those into the cube. And we do this with something called the node compositor. So just like with my Python script, I'm calling this shader script right here. Once I've written this code, which is available on the GitHub repository, I run this script and it will get that ready to go for me to use in my node compositor. So a node compositor is a really interesting tool that's used in 3D graphics. A lot of us in science, we typically write things in some sort of script form where we have inputs as keyword arguments, and then it gives us some sort of output. And we take that output and we give it to the next function or task, and then we build our script that way. That happens in a lot of different areas of science, including my area of astronomy. And what the node compositor allows us to do is it gives us a graphical manipulation of those either scripts or code that is written with an object-oriented language. So that's what we've done here. And just as we've done in the 3-dimensional viewport, I mentioned at the beginning, if you want to add a new mesh or lighting or camera element, I hit the Shift-A button and it will give that to me. If I go over to the node compositor and hit Shift-A, it gives me all of these different 3-dimensional nodes to manipulate 3-dimensional objects and properties of those objects within the compositor. So I can build a visualization scenario with these graph-like elements. So I have my texture coordinates here. I have an object. And what I do is I draw with my mouse from one element, the output of one element into the input of another one. And so one of those elements is going to be the open shading language script that I just showed you. So I can choose here, let me zoom in. I can choose shader script, and then I have a directory of those images that I just ran across the screen. Those are the slices from my CAT scan. I give it a prefix, I tell it what those extensions are. And this box right here, this script box, is actually getting variables from my open shading language script. So I write this bit of code here, this bit of boilerplate code, and then the parameters show up in my GUI over here and I can manipulate them, okay? I have 100 elements of my data cube, 100 slices, or if you were working in astronomy, you have 100 frequency channels. And so that's telling me I'm going to go from frame 1 to frame 100. That tells me how many image elements I actually want to load into the script. Then I have a multiplication element right here. If any of you use Photoshop, this is going to be a common element that you use in any kind of graphics package. Acts kind of like an amplifier. And then I have 2 color ramps. This is going to, and you'll see this in the final visualization, determine what my transfer function is going to be, basically by my color bar scale, but it's going to be doing it in 3 dimensions. So if I have a 3-dimensional data cube, obviously I don't want it to be opaque. I want some sort of transfer function, some sort of transparency associated with that color bar. So while my bottom color ramp is opaque, my top one here, you can see the checkerboard pattern in the background, is going to go from a white to kind of a red, a pinkish color, down to a red, a maroon, black, and then slowly go out in transparency. If you do any graphics work with Photoshop or graphics programs, you know that this is changing the alpha channel for your graphic. We're doing the same kind of thing here, but we're doing it for 3-dimensional volumetric elements, okay? We add another amplifier in, and then we're going to have these volumetric pixels, these voxels, actually emit the color from the color bar scale, okay? And so we'll set that to be an emission, and then we're going to have a material output that is not going to be a flat surface with a texture, but is actually going to be a volume. Okay, so this is all available on the GitHub website and in the PDF tutorial that I've provided you. But this is how we go about building a 3-dimensional transparent data cube visualization in Blender. And it doesn't look too interesting here in the lower right-hand corner where I have my quad view of my top, front, and right orthographic as well as the camera perspective. But if I switch to my layout view and click on view, area, and toggle quad view, I'll show you what this looks like. By clicking in the very upper right-hand corner, there is a viewport shading renderer. And if I turn that on, it will load my data and show me what my visualization will look like. So now, as I move this around, it will render it in low resolution. And then if I release, it will start rendering in higher resolution. And I can do all my usual manipulation controls like zooming in and out of this particular 3-dimensional viewport, okay? So a real nice way to render 3-dimensional data. If I switch off back to my normal solid rendering view and click on view, area, and toggle quad view, you'll notice that there is a circle orbiting the cube and that my camera is actually attached to it. So this is one of the nice ways that in Blender that you can actually animate and record with your camera, your data visualization, in this particular case, a data cube. What I can do with my camera is I can actually lock it onto a circle and then spin the circle around, and basically the camera gets attached to a dolly that will rotate, okay? So if I click on my camera in my scene collection in the upper right-hand corner, I see that previously we had used the physics properties tab. Right below that is a object constraints properties tab. And so there are 2 constraints that I have put on the camera. One, that it's going to follow a path. In this case, it's a circle, but you could chart a path with a spline curve going through whatever visualization scenario you can envision and have it follow that. But not only do I want to have it follow the circle path around and orbit around, I want to actually have it always track to and point at the cube. So if I hit the play button down here at the bottom and keep your eye on the camera, you'll see that the camera will actually rotate 360 degrees over a certain number of frames but all the while always pointing at the data cube. All right, so I've got my user perspective here in the upper right-hand corner. And so I'll hit my 0 key because I want to see what the camera is going to see. And you'll see that essentially is going to rotate the cube. So if I go back to my rendering viewport, it'll show what that looks like. And it will render it in low resolution, but it gives me a nice preview of what I want to be able to have as my final rendering output. So if I go up to this printer icon, which represents the output properties, okay, I can, in this particular case, I have it set to 1280 by 720. I have it set to an AVI JPEG. I'm going to switch that to FFmpeg video. I'm going to switch my encoding to be MPEG 4 with a video codec, a standard H.264 video codec. And now if I go up to the render menu in the upper left-hand corner and click on render and render animation, this will give out a final video input that will be 1280 by 720 pixels. Okay, so let's take a look at what this output actually looks like. I'm going to stop the share and switch to another screen one more time here. And I'll put this is actually listed on the GitHub repository, but I will put it in the chat as well. Okay, so that's the YouTube video that we will play here, and I'll share my screen one more time. Okay, and we'll make this full screen and play the video. And I'll show you another astronomy example as well. And this should play over Zoom. And the first one that we're going to show is the tutorial, very brief tutorial that we did for a 3D galaxy catalog visualization. And if you render out the video, this is what you will see. You can either watch it on the Zoom session or in the link that I provided you. And so in this particular case, I'm going over focusing where the Milky Way galaxy actually is, but you see thousands of other galaxies. And this is why I like to put this blue grid into any visualization scene, because it gives a frame of reference for movement when you're spinning the camera around. And you can speed up and slow the motion of the camera. You can put different keyframes in there as the camera moves around. So the second one we looked at was using open shading language, and this is the CAT scan data that I had loaded before. And this is what happens when you spin the data cube around and orbit with a circle. You can also zoom in and out of the data cube, as I do in this video, and take different viewpoints as I manipulate the camera around. What we do in radio astronomy is that we can actually measure the hydrogen gas of galaxies and actually see what the motion and rotation of those galaxies actually looks like. So this is a dynamic view of spiral galaxy NGC 6946. And this is just another data cube example, very similar to what we looked at before, but this is something that we actually like to look at in astronomy. It's a nice way to actually look at our data in 3 dimensions. So I will stop the share there, and we will go back to Blender. And so let me go back to one of my previous examples, and I will not save that. And I will show you what we'll go back to our particular catalog example. And I want to point out how to do some of the keyframes with the camera. Okay, so I'm back to my first tutorial. It's the catalog blend file in the GitHub repository. And one of the elements that I add, and you won't be able to see it here, or if I zoom in, you'll be able to see it, is there is a small axis of crosshairs that you can see highlighted in orange. This is what's called an empty object. It's a null object in Blender that allows the camera something to focus on, but that will actually not render in the final video output. So what I do with the camera is, so I've got that empty object right here. If I click on camera and then my constraints, okay, I zero out my camera by changing its position to be X, Y, Z of 0, and then rotation of X, Y, and Z of 0. And I do that with my transform menu right here on the right-hand side. And then what I can do is I can select a track to constraint, change my target to be that empty null vector, which is basically just something for the camera to point at that will not render. And then I can change my axes to whatever I want my camera normal to be, basically where my camera is going to be pointing up. And then wherever I manipulate and maneuver my camera, and I'll look here in the top orthographic view, you'll see the camera highlighted in orange, very small there in the upper left-hand part of the screen. I can manipulate this and you'll see the camera moving around, but that normal vector will always point to that empty object, even though you don't see it in the rendering. So one of the things that you can do is you can actually take that empty object, that it's an empty mesh in Blender, and maneuver and animate it during any kind of visualization scenario, and the camera will always track to and follow that object. So, you know, your imagination is the limit here with how you want to actually film your visualization scenario. But that's actually how we can manipulate the camera, and how we can actually add different keyframes by hitting the I key and selecting where we want our actual visualization to be, how we want the camera to point at different things during our visualization scenario. Okay, so I'm going to go and bring up the GitHub repository and point out a number of things as we conclude here, and I will stop the share and share the GitHub repository. So you should be able to see that on the screen. All of the data that I showed you today are available in this repository. And then there's a README file with the demo video that I just showed you, as well as a number of Blender resources. I realize that we've covered a lot of information today, but there are some real nice videos of people who work with Blender all the time in different areas. There's introductions to the interface and how to build some of your first different models and visualization scenes. I've got some links here for the open shading language and how to use it with Blender. There are some also astronomy types specific things with how to manipulate what we call a FITS data cube. That's the flexible image transport system. That's the standard with how we manipulate three-dimensional data, multi-dimensional data for that matter, in astronomy. So it might be of some interest to folks here. That's how I rendered the galaxy that I showed at the end of the video. I've got a number of tutorials on my YouTube channel, and there are also a number of publications that you want to check out. In addition to the things that I've written about Blender, we have a number of different issues with or a number of different articles and an issue with the publications of the Astronomical Society of the Pacific, all about visualization and astronomy that we published a few years ago. And there's some links to the data that I showed today and some of the data cubes. And I also wanted to point out, since this is a standout skills webinar with the Royce Institute, I wanted to mention a number of links here about visualization colorimetry, how you color your data for different audiences, how you can make your data and your plots, whether they're two-dimensional or three-dimensional, look nicer and really make them stand out in publications and in talks that you might be giving at future conferences or colloquia at different departments in your particular fields. So I'm going to conclude there, and I want to thank George and the Royce Institute again for inviting me to give this talk. And George, if anyone has any questions online, I'm happy to.